cardiac activity. So ECG gives us an idea how ANS is affecting our cardiac activity. That is autonomous system, how it is affecting the cardiac activity can be studied by studying the ECG. And in case of ECG, heart rate variability, which is derived from ECG, is widely used as a non-invasive marker to assess autonomic function. So that means to understand the autonomic function, if there is any abnormal function, if there is any misbehavior, to understand this and by a non-invasive technique is very useful. From ECG, we will try to calculate heart rate variability, and heart rate variability will be directly giving us an idea about ANS activities. That is, higher the heart rate variability typically indicates stronger V is high. That means our parasympathetic activity is high. That is better cardiovascular health. And that means if the cardiac vascular health is good, our HRV will be high. Or otherwise, you can say if HRV is high, our cardiac vascular system is healthy. While reduced HRV is often associated with sympathetic dominance and increased risk of heart disease. So if HRV is less, that means my sympathetic dominance is there. That means my heart is not that strong. There is a increased risk of heart diseases. So this is how directly ECG is related to ANS and then to the heart disease. By analyzing ECG signal in relation to the autonomic system, clinicians or doctors can better understand the balance between sympathetic and parasympathetic. The medical people, they try to see how much is the balance between sympathetic and parasympathetic inputs, which controls my cardiac system. This help in diagnosing the conditions such as arrhythmias, that is irregular beats, stress, that is tension when we say blood pressure increases, or hypertension, that is again related to blood pressure. Hence, ECG combined with analysis provide a powerful tool for early diagnosis and preventive cardiology. That means ECG with heart rate variability and to study the autonomic system will definitely help us in diagnosis. That is one. Second, preventive cardiology. We can even predict if there is any abnormality which may occur in near future. So with this background, uh, I will try to discuss in detail, and I have divided my talk in six parts. That is background of the ECG signal, physiology of the heart and HRV analysis and measurement, clinical implications, HRV applications, and finally we will try to conclude. Now, how ECG is generated? So ECG is basically electrical activity of the heart. This is my ECG signal. ECG signal is having PQRST waves. Uh, ECG is basically consists of five wave component P, Q, R, S, and T. And sometimes U wave is also there, but U wave is not certain that it will be there in all the ECG signals. Basically, this ECG wave, there is a correlation between pumping of the heart and the ECG signal. This is electrical signature of the heart. So heart has two functions. One is the electrical signature. Second one is the pumping mechanical action. So when a particular portion is excited, the muscles try to contract. When the muscles try to contract, they will try to squeeze that chamber. When that chamber is squeezed, blood will try to flow from that chamber to somewhere else. So this has a correlation between ECG signal and mechanical activity of the heart. Atrial excitation. Heart has four chambers. All of you must be knowing. Two atrias are there, two ventricles are there. Atria, that is right atria, left atria, right ventricle, left ventricle. Now, when atria is excited, when right atria is excited, this is with respect to P wave. When P wave arrives, right atria excitation will take place. And when right atria excited, it will try to squeeze and it will push the blood from right atria to right ventricle, from atria to right ventricle. Similarly, when atrial systole, that is blood output, when squeezing takes place, when this squeezing takes place, my Q wave is generated. And during relaxation of atria, my R wave is this peak. This is the highest. This R wave is generated. So similarly, you will see in case of ventriculars also. When ventricular, right ventricular excitation is there, my S wave is generated. And when ventricular systole is there, T wave is generated. And when it is diastole period, my U wave is generated. Both atrias, left and right, contract simultaneously. Both ventricles, left and right, they contract simultaneously. Now, this is basically a correlation between electrical activity of the heart and mechanical pumping of the heart. And if there is any abnormality in the mechanical function, it will be reflected in electrical signal. So that is how the ECG signal, which is electrical signature of the heart, is helpful in diagnosing if there is a fault in the cardiac system, any pumping action if it is there. If the pumping is not strong, the peak value may change. If the pumping is delayed, the duration x-axis may be more important. If pumping is not strong, y-axis may be more important. Like an electrical engineer, we know that x-axis is time, y-axis is amplitude. So both time and x-axis, that is time, and y-axis, that is magnitude of these pulses, are important. And how ECG is measured? Basically, we put 6 electrodes on the chest. These are the precordial electrodes. So this is V1, V2, V3, V4, V5, V6. 6 electrodes we place on the chest. The location of these electrode is V1 is fourth intercostal space, right of sternum. So this is right of sternum. This is intercostal space. One, two, three, fourth. Fourth intercostal. Generally, doctors, with the help of fingers, they try to see the ribs, they count, and then it is placed on fourth intercostal place on right. And V2 is fourth intercostal place on left. This right is corrected. It is left sternal border. Similarly, V3, V4, V5, V6 locations are there. And 4 electrodes we placed on extremities, 2 on arms, that is left and right arm, and 2 on legs near the foot, right foot and left foot. So 10 electrodes we place on the human body, and we record a ECG signal. And we will get 6 records from the chest, precordial leads, that is V1, V2, V3, and from the upper extremities, that is from arm and foot, we also get 6 electrodes, 3 bipolar and 3 unipolar. So anyway, I will not go into the detail. You may go through. Now, regarding the ECG signal, our interest is the magnitude of the ECG signal, this wave, magnitude of R wave, P wave, Q wave, that is down minus, S wave, T wave, and U wave. Second one is the duration of the wave. So P wave start from this point and ends at this point. So each block, this duration, this small square is equal to one small square is equal to 0.04 second. That is 40 millisecond. And this bigger square means it is 0.2 second. And all the five bigger square, 1, 2, 3, 4, 5, this whole length equal to 1 second. So roughly one ECG signal is equal to 1 second, roughly. So this indicates that 60 beats per minute. This is one cycle. One cycle is roughly 1 second. And similarly, magnitude, this one block is equal to zero point 0.1 millivolt. So if it is 5 block, it will be 0.5 millivolt. And one this from this point to this point, that is two blocks, two bigger block is equal to 1 millivolt. That is 1 millivolt. So this is how we just try to measure the peak and along x-axis the duration of each wave. So we have 5 waves P, Q, R, S, T, and 6 one is U. And then we have interval, PR interval, QT interval, QRS interval. So these are important from the diagnosis point of view. And this is when ECG machine is recording, the speed of recording is 25 millimeter per second. So this 25 millimeter will be equal to 1 second, or this 1 second is equal to 25 millimeter. That is if the paper record is there. So in case of ECG, I have already told you P, Q, R, S, T, and U waves, and PR interval, QT interval, QRS interval, and ST segment is also important. And there is a J point, this J point, this J point. So whether this J point is up positive or negative, this also has significant information with respect to cardiac disease, cardiac problems. Now, then important is P wave, QRS, Q wave, R wave, S wave. There, one is magnitude, second one is duration, third one is their shape, that is morphology. Whether P wave is positive, whether it is negative, whether it is biphasic, positive then negative, or biphasic, negative then positive. So this is important. What is the shape of each wave? P, Q, R, S, and T wave, duration of each wave, and magnitude of each wave. So these are the various shape of morphology of QRS, QR, QS, R wave, etc. These are the various possible configurations or morphologies. Now, another important point is rhythm. See, one is the duration, magnitude, and morphology of each wave. Another one is between RR interval. This is one R peak, this is another R peak, this is another R peak. We say, what is the heart rate? What is the pulse rate? So this pulse rate, whether this pulse rate is within normal limits, that is normal sinus rhythm. This is basically rhythmic. Whether it is a normal rhythm or if it is not a normal rhythm, then what type of abnormality is there? So that comes under arrhythmia. There is another uh, disease which we say if the rhythm is not normal, then whether it is tachycardia or bradycardia, these are the clinical names. So whether the heart rate is very high, whether heart rate is very less, whether there are missing beats. So all this information is also important from diagnosis point of view. So in this particular diagram, you will see that this duration, the duration changes between each R to R peak. Duration is not constant, but change is very small. Change is very small. So heart rate is between 60 to 100 beats per minute. Rhythm is regular. P wave is always before R wave. This is P wave, then R wave. P wave followed by R wave. So P wave before each QRS. PR interval is within this particular range, 0.1 to 2.2 second. That is this P to this R interval. And QRS interval is less than 0.12. This QRS interval. This QRS interval. So this is another information which is required from the diagnosis point of view. Now, this is arrhythmia. As I was mentioning, if the heart rate is not within the limits. So usually heart rate is 60 to 100. In this case, heart rate becomes very less. This is heart rate becomes very less. And here heart rate becomes very large, very high. So if rhythms are irregular, then it is a case of arrhythmia. So we try to find out the problem or issues are with respect to rhythm. Number two, with respect to morphology. Number three, with respect to magnitude of each wave. Number four, with respect to duration of each interval or segment. So four things we try to measure when we have an ECG signal. Now, what is the science behind this HRV? Heart rate variability. That is, heart rate variability is how heart rate is varying. That is, how interval between two consecutive RR waves are changing. You must keep in mind that normally we say that my heart rate is 60 beat or 70 beats per minute. This 70 beat is not constant. At one particular moment it is 70, the next second it may be 72, the next second it may be 68. This heart rate is continuously changing, and this change in heart rate, how heart rate is changing, in 1 second it is 68, next second it is 70, the next second it may be 65, the next second it may be 72. This variation in heart rate from one beat to another beat is nothing but it is my heart rate variability. This also has information. We have discussed 4 points: magnitude, duration, morphology, rhythmic, and another one is interval between two consecutive heart beats, or you can say RR interval. So that is HRV. So five components are important whenever we want to study, whenever we want to do the analysis of ECG signal. The science of heart rate variability. Now I will concentrate mostly on heart rate variability. What is heart rate variability? General concept is heart act like a metronome. Metronome means it has a constant rate, that is 70 beats per minute, which is incorrect. It also keep a strict cadence. It has a fixed rhythm. Rhythm means it only goes from 60, 61, 62, then 70, 71, 72. This type of rhythmic is not here. It is not following it is rhythmic, but it is not a strict rhythmic or strict cadence. Whereas reality is heart beats through a wide spectrum. Through a wide spectrum means heart may beat between 60 to 100 beats per minute. Sometimes 60, 62, 70, 72, depending upon my body reaction. Whether my body is, a person is running, his heart rate may be more. A person start thinking, his heart rate may increase. A person is relaxing, his heart rate may go down. So these beat to beat variation is science of heart, HRV. So beat to beat variation is science of HRV, which we will discuss in this lecture in detail. Otherwise, rest of the parameter you can directly measure, and then we can use those parameter for evaluating the heart health or health of the cardiac system. In case of HRV, in stress condition, when a person is under stress, he has some pressure on his mind, heart rate variability is lower. This variation between two RR interval becomes less, and it behaves like a metronome. The variation becomes so less, it is almost a constant heart rate. This is indicative of higher sympathetic nervous activity. I discussed with you, I told you that we have autonomic system where we have sympathetic and parasympathetic. Higher sympathetic indicates that my heart rate is lower, heart rate variability is lower, and a person is under stress condition. So that means it's a good information when higher sympathetic nervous activity is there, my heart, it is a stress condition, my heart rate variability becomes low. So response is like fight or flight. So person start thinking कि मैं भाग जाऊं और मैं कूद जाऊं. Immediately he wants to take some sort of action. Whereas during psychomental stress, psychological stress, when a person is under fear, डर है उसको, गुस्सा है, anger, frustration, depression. In all these cases, the sympathetic nervous activity increases, and decrease of activity of parasympathetic decreases. That is, relaxation is less and sympathetic is more. So this leads to increased risk of fibrillation, chances of arrhythmia is more, irregular beats is more, stress level on the heart increases, it affects our hormonal and immunological system. तो हमारा हार्मोनल सिस्टम डिस्टर्ब होगा, हमारा डाइजेस्टिव सिस्टम डिस्टर्ब होगा, हमारी इम्यूनिटी पावर भी कम होगी. All of these take place along with a slow and disordered change in the heartbeat. एक तो one is heartbeat changes are slow and disordered. Whereas on the other side, during a well-being, when a mind is relaxed, sincere appreciation and love, parasympathetic activity increases, leading to a strong and ordered decrease in heartbeat. So heart HRV will be high, strong, and there will be a not a random, it will be a ordered decrease in the heartbeat rate. Heart rate will decrease, but there will be a systematic or uniformity will be there. Regularity will be there. It will not be random. And this is a positive effect to the cardiovascular, immunologic, and hormonal system. This is plus point. So if somebody say that my heart beats between 60 to 80, 60 to 80, and average is 80. So this is considered healthier. Then a person, if average is 80, but heart beats between 75 to 85. So range is 75 to 85. Average is same 80-80. So in this case, this heart is not healthier. Heart where range is more is healthier than a heart where range is less. And people say, or as per the medical study, with the age, this range decreases. That is why in old days, people say that don't give a shock to your grandfather, grandmother, etc., because their heart rate variability decreases. So they will not be able to bear the shock. So heart rate is basically RR interval, cycle length, heart period variability, RR variability, RR interval. All these are, you can say, related terms. They are same. So heart rate has applications like it can has assist to the functional health of the body. Normal functional health of the body can be assessed. It can pinpoint a specific medical condition. Under different medical condition, HRV changes. Monitor the effectiveness of ongoing therapy. When a person is given medicine, like sometimes we give medicine or doctors give medicine to the patient to reduce the stress. So you can measure the heart rate variability and you can see whether that medicine effect is there or not. Fitness level can be tested. Risk-based segregation of cardiac patient, you can divide in various groups on the basis of HRV. And HRV is affected, that is the autonomic system. When this parasympathetic or sympathetic activities are high or low, they affect our five respiratory system. Our respiratory rate may increase or decrease. Vasometer, motor, that is blood pressure, blood flow, blood pressure. Thermoregulatory, that is sweating, etc. Renin, angiotension, that is kidney system. Central nervous system, our brain or central nervous system. So these five systems, they will be balanced between sympathetic nervous activity and parasympathetic nervous activity. Finally, they control the HRV. So sympathetic branch accelerates the heart. Parasympathetic or vagal, it is also called vagal branch, slow the heart rhythm. So sympathetic inputs are given to brain, then a balance will be obtained, a signal will be generated which will try to balance this by controlling these five systems by the brain, and cardiovascular system will be the output control on the cardiac system, and our whole system will behave like a closed loop. So this will decrease or increase. Similarly, sympathetic will increase. Similarly, barometric, that is vagal, that is parasympathetic, will increase or decrease. And finally, this will try to reduce, try to increase, and a balance will be generated. So you can say by all these inputs will be given to brain system, they will generate parasympathetic signal, sympathetic signal, then blood pressure will be generated and HRV signal will be generated. So sympathetic speed up heart rate, increase heart rate, heart contraction. Heart contraction will be more. Blood pressure will increase. When contraction increases, blood pressure increases. And this also increases with exercise. If you do exercise, same thing may happen. When you are under a relaxed condition, not doing any exercise, or when you are doing exercise, similar action will be there. Parasympathetic, it slow down the heart rate, decrease heart contraction, decreases blood pressure, and this increases with the rest. Increases means relaxation will increase. If we are resting, heart rate will become more slow. If we are resting, heart contraction will be much less. If we are resting, blood pressure will also go down. So that is why when a person is under stress or person is having high blood pressure, doctors advise, ask the patient to take rest. So a balance is important between sympathetic and parasympathetic. Now, how HRV is helping or giving us an idea about the health, we try to find out balance, that is SNS drive, parasympathetic drive. That is, in our signal processing, we will find out low frequency power and we will find out high frequency power. Ratio of this health of the cardiac system. We will discuss what is this LF, what is this HF. So finally, HRV we will use to identify to classify the heart, whether it is under stress or under any disease condition by measuring these parameters, which we will discuss. So basically, this is my ECG signal. So in case of ECG signal, I will try to measure the interval. I will convert this ECG signal into heart rate variability. So this first T to R interval is 1.017 second. Next interval is 1.014 second. This is third interval. This is fourth interval. So this, if I plot this interval in time scale, so this will be 1.017. This is 1.014. This is still less. This is still less. Maybe 1.01. So this is my heart rate variability signal. This is my heart rate variability signal. This is my ECG signal. So this is ECG signal. This is heart rate variability signal. So we will try to analyze this signal rather than this signal for HRV study. I told you that in HRV, five uh, systems work, mostly body temperature, that is thermoregulatory, blood pressure, that is vasomotor action, and respiratory, that is respiratory system of the body, respiratory system of the body. So respiratory system has frequency 0.2 to 4 hertz. Blood pressure changes. These are all changes. Blood pressure changes have frequency in the range of 0.1 hertz. Body temperature changes are 0.05 hertz. So slowest is body temperature change. Blood pressure changes slightly faster than body temperature. Respiratory changes are very fast as compared to blood pressure. So you must have seen when a person is under sudden shock, immediately his body temperature will start increasing. He will get sweating. So thermoregulatory system immediately react. Sweating will be there. His blood pressure will start changing, will become high, and respiratory, he will breathe more fast. So kidney function will also be there, and he will start feeling an urge to go for washroom. So that is how the body is trying to make the balance between sympathetic and parasympathetic, and that is our study. Sympathetic increases low frequency power. When low frequency power increases, if we do the frequency domain analysis of HRV signal, you know, you are an all are mostly must be knowing about time domain signal and frequency domain signal. This is my time domain signal, and if I find out Fourier transform, I can get frequency domain signal. So in frequency domain, low frequency power increases with sympathetic increase, high frequency power increases with parasympathetic power increases, and ratio between two spectral power describes autonomic balance. So like if you give RR interval time series, like if you give a light to a prism, the output will be 7 color. If white light is given to the prism, output becomes 7 color. So prism is my FFT. Prism is my FFT. You give times data, it will give you frequency output. So, so these are the FFT of the HRV. So this is very low frequency, this is low frequency, this is high frequency. In case of HRV, very low frequency is from say almost 0 to 0.04 hertz, 0.04 hertz. And low frequency is 0.04 hertz to roughly 0.14 hertz. And very high frequency is in the range of 0.13 hertz to say roughly 0.2 hertz. So this is the variation in power spectral function of the HRV. So we can do the analysis of HRV. I will give the slides definitely. I will give the slides in the end of the lecture. Somebody has asked whether slides will be available or not. time domain analysis, frequency domain analysis, non-linear analysis. So I will just give you an idea about time domain and frequency domain because we are short of time. So time domain, we study short time variability and long time variability. One is for 0.5 second, 0.5 minutes, another one is 5 minutes. So 0.5 minute means in 1 minute we have 60 to 70 beats. 0.5 minutes means around 30 beats. When we study 30 beats, normally it is a short term variability study. When we study 5 minutes means more than 300, it's a long term variability study. So we have two types of studies, one short term variability, another long term variability. So we try to find out standard deviation. This is standard deviation of normal to normal. See, when we are studying HRV, we have to keep in mind I am not concerned about the magnitude of the ECG signal. I am not concerned the time interval between various wave components. I am only studying the rhythmic behavior of RR interval. So that is why I am saying that standard deviation of normal to normal beats, that is RR interval. So RR interval should be normal to normal. Normal to normal means if they are between 60 to 100. If it is more than that or less than that, then it is a case of arrhythmia or it is a case of missing beat. That is a separate study. So this HRV is only limited to normal beats. We find out standard deviation. We find out average of the standard deviation. We find out RMS value of the standard deviation. Then we calculate normalized value, standard deviation, index. That is mean of standard deviation of all NN intervals for 5-minute segments. So we just try to average. Similarly, standard deviation of standard deviation. So standard deviation, if you recall your earlier, whatever you have read, basically standard deviation is nothing but it is an AC component. It is an AC component. It is basically velocity, change in distance. And standard deviation of standard deviation, it is an acceleration. So you can say distance as standard deviation is velocity and standard deviation of standard deviation is acceleration. This is a double differentiation sort of thing. So we calculate these parameters. In frequency domain, we calculate very low frequency power, that is 0 to 0.04 hertz. Low frequency is 0.04 hertz to 0.15 hertz. And low frequency normalized value, low frequency power divided by total power minus VLF. VLF we take out. Total power minus VLF is low frequency normal value. High frequency is total power in the range of this. High frequency normal will be high frequency divided by same value. Total minus VLF, and ratio is low frequency by high frequency. So we find out the spectrum of the signal, HRV signal, and then we calculate these parameters, VLF, LF, HF, HF normal, and ratio. So these are my spectrum of the signal. This is how we record ECG signal. This we have done in the lab also. These are the process we followed. So when we record ECG signal, then we do digitization of the signal. So normally the signal frequency is 0.05 hertz to 150 hertz. This is our frequency of interest. This is maximum frequency range which may be of interest to study. Now, if the highest is 150, then sampling frequency should be more than double the highest frequency. So CSE, Common Standards in Electrocardiography, UK, they have recommended this sampling frequency to be 500 hertz. And some people, they have recommended sampling frequency of 1000 hertz. Actually, when our processors were not that strong, our memory was not that high or easily available. So sampling frequency was 500. Now when memory is easily available or processing speed is high, so more samples we collect by having sampling frequency to be 1000 hertz. So resolution becomes high. So different regulatory bodies or people who are studying ECG, they have recommended a different sampling frequency, but it is recommended that minimum should be 250. Now, this is how we detect the R wave. Once we detect the R wave, then we calculate, that is QRS detection. We have done QRS detection in the lab. Many people with me, they worked in the beginning around 2000 when neural network just started. So they used neural network to detect the QRS complex. So RP, that is our very basic paper, and it has good citation also. Neural network for detecting the QRS wave. And so you can use any method. So this is my R peak. So this is RR, R peak, R peak, R peak. So this becomes my QRS event, and this becomes my RR interval. This interval is RR, this interval is RR. Now here you will find that when we do time domain analysis, we feel that these interval, one sample we take at this, another, if the sampling frequency is 1000, that means this sample, the next sample we should take after 1 millisecond. 1000 hertz means 1 millisecond. So 1 millisecond, another after 2 milliseconds, then 3 millisecond. Whereas in this case, the samples are available. This may be one, you can say second. This can be 1.1 second. This may be 1.01 second. This may be 0.9 second. So this interval is not constant. This interval is not same. So we have to interpolate. We have to do the sampling. If we want to go for time domain analysis or frequency domain analysis, we have to do the sampling in such a manner that we have each value after a certain fixed interval depending upon my sampling frequency. So either I can just interpolate, say if this interval is 1 second, total 1.1 second, I will measure this value. This is the start point. This is after 1.01. So I will measure what will be the value after 1 millisecond, then after 2 millisecond, 3 millisecond. Like that, I can calculate the magnitude. So that will be my resampling of the HRV, enable synchronization with the physiological signals. Various task force, they have recommended various methods. So they have used previously sampling frequency to be 8 hertz, 7 hertz. 500 hertz is the sampling frequency for ECG signal. And because HRV signal, I have told you, HRV signal is very low frequency signal. HRV signal, you will find that HRV signal is having up to 0.4 hertz. 0.4 hertz. So sampling frequency should be roughly more than double of 0.4 hertz. So we go up to 0.4 hertz. So sampling frequency should be more than 1 hertz. HRV sampling frequency is in the range of 1 hertz. ECG sampling frequency is in the range of 500 hertz. These are two important points. So you will see that various people, they have recommended sampling frequency of HRV signal 1 hertz, 1.2, 2, 2.17, various research papers. And we have done our study also. We have used 4 hertz sampling frequency. Then there is another function, the research component in this case. What should be the sampling frequency? That is one thing. Second thing, what type of window function you have to use so that aliasing is not there. So we have used different window function. Many people have done work in that area. They have used different window function, different sampling frequency, and optimal sampling frequency and window function has been selected. These are some of the results with respect to that. You will find that in case of subject 1, a sampling frequency 2 hertz, 4 hertz, 6 hertz, 8 hertz, 10 hertz. Then we calculate all the values, low frequency, high frequency power. These are very low frequency power, low frequency power normalize, high frequency power in millisecond. This is a frequency range. This is a power in millisecond square. And similarly, low frequency by high frequency ratio. So we find that when the ratio becomes almost constant, say 2.707, 2.701, up to 2 or 3 decimal, the value is same, we feel that this sampling frequency should be taken as the best sampling frequency on large data set. See, this decision is generally taken sometimes by judgment. Sometimes we divide a method that when the sampling frequency in more than 50% of the cases, the ratio between PL or PHF is within 0.1% or 1%, that sampling frequency is good for my work. This is how we try to do it. So similarly, so many research papers you will find where they have used different segment length of the window, that is Henning window, Hamming window, tapered, cosine window, and similarly sampling frequency 4 hertz, 10 hertz, 5.1 hertz. So similarly, the research scholars with me, they worked with different sampling frequency, with different window function. Our purpose was that it should be best, the result should be best, and the time spent, or it should be fast. So these are some duration. The measurement depending upon various sampling frequency. This is various duration, window width. Window width 32 samples, 64 samples, 128 samples, 250. So those who have an idea of signal processing, they will understand better. But others, they have to go through signal processing tools also. Now, again, along with this heart rate variability, that is ECG, RR interval, respiratory variability and blood pressure variability is also important. To study a correlation between respiratory variability, heart rate variability, and blood pressure variability, this whole thing gives a much better idea of my autonomic nervous system. So that is where then we extended our study with respect to respiratory signal as well as blood pressure signal. Blood pressure, that is systolic blood pressure, diastolic blood pressure, as well as mid blood pressure. So we try to, this is RR variability, this is RR signal, so this is power spectrum. Another thing we try to find out, that is point care plot. See, in time domain, we are measuring a variation. I told you two types of variation, one short time, another long time, one for 0.5 minute, another for 5 minutes. So time domain analysis gives me idea of changes in the heart rate over a period, within a period of 0.5 minute or within a period of 5 minutes. And similarly, depending upon that, my frequency domain analysis here. But I am not able to study beat to beat. For beat to beat, we study point care plot. Point care plot, that is first beat I plot here, that is 760 millisecond. Second beat I plot on the y-axis. Here it is 780 millisecond. So this is one point, this is another point. Similarly, this point, this point, this point, this point. Like this, we will have, these are the point. And we make a elliptical circle. We make a elliptical circle like this. So this is my systolic blood pressure variability. This is signal. This is for time domain signal. This is frequency domain signal. This is point care. I will give you an idea. that how this point care plot is useful. This type of chart is prepared by the standard machines, those who give HRV analysis with respect to heart rate, with respect to blood pressure, with respect to respiratory rate. So they will give you tachogram, they will give you spectrogram, they will give you point care plot. Along with some values, here you will find on the right hand side, they will write name, etc., code number, etc. Then average heart rate, average blood pressure, average respiratory rate, all these parameters will be displayed on the right hand of the graph. So this is diastolic blood pressure, this is median blood pressure. So all these plots are plotted. Now we use wavelet also for this analysis. That is for the Fourier transform analysis. See, this is my signal. First, I use high pass filter and band pass filter, a low pass filter by selecting a particular wavelet. So GZ is my high pass filter, HZ is my low pass filter. This is how discrete wavelet transform works. If people have signal processing idea, they will understand this DWT decomposition. So if my sampling frequency is 4.8 hertz, frequency output will be 1.2 hertz to 2.4 hertz, because my signal sampling frequency is 4.8 hertz. My highest frequency will be up to half of this, that is 2.4 hertz. So high pass filter will give me 1.2 to 2.4, and low pass filter will give me 0 to 1.2. Again, if I apply high pass filter on this, this will give you 0.6 to 1.2, and this will be 0 to 0.6. 0 to 0.6, again I will get 0.3 to 0.6, and similarly 0 to 0.3. 0 to 0.3 will give me 0.15 to 0.3, and so on. So you can say the output D7, this D7 output, this D7 output is directly my very low frequency signal. D5 plus D6 will be my low frequency signal, and D3 plus D4 will be my high frequency signal. D3, D4. So these signal will directly give me power spectrum of the heart rate variability by using discrete wavelet transform. So we use that also. We could get a good result in this case also. So this was the diagram. This some of the wavelet transform which people have used. This is the list of those wavelet transform. These are the results. We used tested our all HRV applications or development. We had Fantasia database. This is basically to compare the various algorithms. They have given this database. Now, Y indicates young. So FLY01, first young candidate, second, third, fourth. So we calculate similarly RR interval time. This is for 5 minutes, roughly 300 seconds. This is around 300 seconds. 5 minutes means they took RR interval, complete RR interval, because next RR interval may not be there complete. So within 5 minutes, uh, we have 298 where we could get to 359 RR intervals. Maximum and minimum, then ratio of maximum and minimum. So all these parameters we calculated, we discussed, that is SDNN, SDSD, RMS, SD, all these parameters we calculated for a people of young 21 to 34 years old. And we compared with the values available in that database. So this is for older people, 68 to 85. Here you can see that standard deviation in this case is 31, in the range of 3154, and standard deviation in this case is 58. It is 83, much more. So you can even compare for younger people, the variation is 3410. Variation is large. Variation is large. For older people, O means older. The variation is less, 691, 1018. So when age increases, the variation decreases, and in certain diseases, this variation is affected. If a younger people should have this range of variation, then with the disease, in case of younger people, this variation may change. This is again Fantasia database for older people. This is spectrum and same. First was the time domain analysis. This is frequency domain analysis. That is low power by high frequency power, this ratio. So this ratio you will find for younger people, it is less, 0.25, 0.8. For older people, it is more. So it is less means their high frequency component, parasympathetic is more. Low frequency component is also more, but the ratio becomes quite less. And in this case, ratio is large. And if the ratio is high, that means it may not be a normal person. There may be some abnormality. So point care plot indicates beat to beat variation. This beat to, if this beat to beat variation, if this particular exchange, if it is more, then we say it is variation is large. It is a young person or it is a healthy person. If this variation is less, it is not that healthy. It is for normal because scale is like this, only from the scale point of view. But otherwise, we just measure SD1, SD2, SD. And under some disease cases, all the points will be very close to each other. It may not be in the form of a wide range. So different pathological conditions, we can have different plots. For younger group, this ratio will be different. And for various database, we studied this. And similarly for the blood pressure variability, for young people, for old people, the power, low frequency power, high frequency power, you can directly see that in this case, this is more, this is less, low frequency. So ratio you have to find out. Ratio is important. Low frequency by high frequency, this comes out to be 8. This comes out to be much less. So various pathologies, various diseases like myocardial infarction, in this case, cardiac transplantation, diabetic neuropathy, myocardial dysfunctions, and clinical use is there in all these diseases. HRV, depressed HRV can be used as a predictor of risk after acute MI and as an early warning sign of diabetic neuropathy. I told you it is also used as a predictor. So HRV value can predict risk factor in acute myocardic infarction or in case of diabetic neuropathy. In both these cases, these are some normal values which we can compare. So same analysis we can do with the help of AI also, which some of my students, they have started doing and they are working, they have got good result. So I will not take at this particular point. So these are some of the PhD students. They have done 1, 2, 3, 4, 5, 5 PhD plus 3, 7, 8 students have done PhD on this topic by using various techniques. So this was some video on heart rate is not required at this moment. So I thank you all for your patience, for your listening to this lecture very patiently. Not many questions were there in between. So I am open for any query, question. Anybody having any query, question? Any question?
Yes, participants, if you have any question, you can write down in the chat box. Okay, can we use ECG for meditation? Okay. Manish Patel, sir, he has asked that can we use ECG for meditation level check?
A, uh, it should not be an exercise. Breathing, fast breathing, slow breathing, With respect to fast breathing, slow breathing, we can definitely study whether the variability is high or low. Only with respect to that condition we can compare. But we cannot compare from rest condition to a exercise condition, because in both the cases our heart rate will increase. So variability will become less. So this I have not tried in that. We have to look into that, because when heart rate becomes large, variation becomes less, then how the result we will try to interpret from the cardiac disease point of view. It's not that simple in that case.
Okay, thank you, sir. Is there
Well,
any further
definitely
question?
we can use under meditation, we can use it, but then we have to compare a person's heart rate variability, how it is improved by meditation. Today you take, and after 10 days, after 50 days, after 3 months, then you can compare if the heart rate variability is improving. Then you can say that this meditation has a positive effect.
Okay, thank you, sir. Is there any further question? Yes, we will share the PPT, so there is no problem. We will share the PPT. Even that recorded video will be also shared with you. So there is no issue with that. Okay. Yes, any further question? Okay. So if not, then thank you, sir, for spending time with us.
Okay, thank
One
you.
more
Thank you,
question,
Amit.
sir.
Thank you.
Sir, there is one more question. Not more.
Yes, yes. Can
See,
we drive blood pressure from ECH signal waveform? See,
ECG.
this is a ECG. See, this is a very question mark question. These days, watches are coming. Even you must have seen in the market that just by pulse, they are measuring the ECG signal. They are measuring ECG signal. They are even measuring the blood sugar level. But none of these device has FDP approval, that is a Food and Drug Controller of US. None of these devices have approval from them. Definitely people are working on that. Even in the market, equipment is available. They record ECG is available. ECG on Apple Watch is available. Arrhythmia detection is possible, and this has the approval of FDA. FDA approval for Apple Watch in case of ECG for arrhythmia detection is there. But from ECG to blood pressure, from ECG or from the pulse to blood sugar level, these are all under research. Point of care equipment are being developed so that directly, without any invasion, the blood pressure, ECG, and blood sugar can be measured, like pulse rate, etc., without pricking. But still there is no technology which has the approval of FDA or regulatory body of India or any other country.
Okay, thank you, sir. I think one more question Monica has asked. How can
Uh,
ECG be used to diagnose myocardial infection?
See, in case of myocardic infarction, your T wave becomes inverted. This is a very common. Directly when a person goes to a doctor, he will say that there is a infarction, means some of the fibers are dead. So which location, all the 10 ECG wave component, when they see, that is lead 1, lead 2, lead 3, and L1, L2, L3, AVR, AVL, AVF, they can directly see that whether the infarction has taken place or not. It is very standard, very commonly used. This is probably one of the very early tests to see the myocardic infarction.
Okay, thank you, sir. Uh, so with this, we are ending up our first session for day 2. Sir will be joining us tomorrow as well from 6 to 8. So if any further question is there, maybe you can ask tomorrow with the sir. So with that, we will take 5-minute breaks. Okay. So maybe at 6:25 we will start our next session. Thank you, sir, for joining us.
Okay,
See you
thank
tomorrow.
you. Thank you. Thank you. Thank you.